Bonjour à tous. Welcome everyone. Welcome to the weekly IAP colloquium. So today it's a real pleasure to host Marco Cirelli. Marco obtained his PhD from Scuola Normale Pisa in 2004. Then he went to postdocs at Yale University for 3 years, and then not far away, IPHT CEA Saclay for a year, and then he became a skin-RS researcher at IPHT first, and then at LPTHE since 2015. During that time, he was also a fellow at CERN for a few years. Marco has a broad range of expertise and interest in astroparticles, physics beyond the standard model, cosmology, in particular dark matter and neutrinos. He's also a very active scientific member of the physics community. So he's been organizing many schools, conferences, and he's still a few months the president of the physics department at Sorbonne University. Almost.
Scientific
the scientific council, sorry, of the physics department. Today, recently you wrote a comprehensive review about dark matter, and so today it's a pleasure to you taking this overview for 1 hour and then questions.
Okay. Thank you very much, Sebastian, and thanks everybody for being here. So indeed, what I'm going to do today is to try and present, and I should click probably on this, try and present a sort of overview about dark matter and about what is it that the dark matter candidates that we are still exploring today. So the idea is to do something starting from the basics in some sense. So I know that in the audience there are some super experts on the field of dark matter, and some things that I'm going to say are very well known, but I thought it was a good idea to state how much we know about dark matter, or actually how little we know about dark matter, and what are the current ideas that people are exploring. Okay, so interrupt me at any time, of course, if there are questions and comments and curiosities, and I'll be happy to try to answer. So let me start in the following way by just giving an executive summary in 2 minutes of what we know about dark matter. As you will see, it's not much, and it has to guide our knowledge about the field. So the thing is that we know that dark matter exists. Okay, so far no objections. Because of this, and this, so galactic rotation curves, weak lensing and clusters of galaxies, and precision cosmology, meaning the CMB, large-scale structure, and so on. So dark matter, in the sense of an extra ingredient in the matter fields of the particle physics, works at all these scales. Let's say that this is the assumption we take. It's not the only possibilities. There are possibilities of modifying gravity to fix those anomalies, say, but let me stick to the case that dark matter is a new ingredient of nature, and it exists because of this, and this. So very different scales, very different phenomena explained by just adding an extra ingredient. So indeed, we think that it's a new and unknown particle, where by particle I mean something that behaves like matter in cosmology, so it dilutes as 1/3 the volume of the universe as the universe expands, nothing more than that, but also nothing less. And it's a new and unknown particle in the sense that the particles in the standard model cannot fulfill the properties that I'm going to give in a minute. Okay, so we need something extra. So we also know that it makes up 26% of the total energy budget of the universe, and 84% if we restrict only to the matter budget of the universe. This is given by this number here, measured notably by Planck and the CMB. So notice how small the error is. We know very well how much dark matter there is. We just don't know what dark matter is, of course. We also know that dark matter has to be a particle, or more generally a body, which is neutral, meaning no electric charge or very little electric charge. So that's why we call it dark. It doesn't interact with light. It has to be cold, meaning that it has a momentum which is much smaller than its mass at a crucial moment in cosmology, which is the moment of the CMB formation, and then by extension also later in the history of the universe. So it moves slowly, it's non-relativistic, and so it's cold, forming structures at larger and larger scales. It has to be very feebly interacting with itself and with ordinary matter. And that sometimes is, the definition is, the word which is used is collisionless, but I don't like it too much because it means that we have no collisions at all. And so what I'm going to discuss later concerning experiments will be hopeless. So let's say that it has very feeble interactions with itself and with ordinary matter, where by feeble, I just want to be agnostic and say something which is, say, feeble. It can be the weak interactions of the standard model or something similar or weak. And we will see later some examples. And finally, it has to be stable, meaning that its half-life is at least longer than the age of the universe, much longer the age of the universe, which is 10 to the 17 seconds. So these are all the properties that we know, essentially all of this, but no more than this. We also think that it's possibly a relic of the early universe, so a particle produced in the early universe that has survived in some way. We'll see an example later. And we search for it in the three standard strategies, which are direct detection, meaning waiting for a particle of dark matter to scatter on a standard model particle, typically a nucleus in an underground experiment, or indirect detection, so looking for the annihilation of two dark matter particles into standard model particles, say gamma rays, or colliders, meaning producing dark matter particles from the collision of, say, two protons at the LHC. So this is the standard lore of how to search for dark matter. Now, if you look at this, so in 4 minutes, okay, it's all we know about dark matter. And what sticks out immediately is that there is no information about its mass, nor about its charging interactions. Okay, charging interactions in some sense, yes, in the sense that I said something negative, so these interactions cannot be too big and the charge cannot be too large. But about the mass, there is absolutely no indication, right? So the issue is that cosmology doesn't tell us whether dark matter is made of a huge number of very light particles or a very small number of extremely heavy bodies. So this makes the whole difficulty of this business. So to be more quantitative, if you draw famously a range, a diagram of the range of possible masses for dark matter candidates, you discover that you can cover something of the order of 90 or 92 orders of magnitude. So from these ranges to these ranges. So as a famous theorist in the US likes to put it, the hard work of thousands of theorists for about 40 years has restricted the range to only 92 orders of magnitude, which is a great achievement. So as you see, there are three main areas here. So there are macroscopic bodies above the Planck scale, meaning that any particle which is heavier than Planck scale has to be a composite body, otherwise it would become a black hole. There is then particles, which can be elementary or composite, but let's say something that we can treat like particles. And at very low masses, it's better to talk in terms of classical fields rather than particles. There is no clear distinction here. So the description is always in terms of quantum field theory here. But if the body, say, is heavy, it's better to consider it as a particle. If the body is light, it's better to consider it as a classical field. Exactly like if you are treating photons in the photoelectric effect, it's better to talk about one photon hitting the metal. If instead it's radiation, it's better to treat it as a classical field of light photons. So probably all of you know this, but let me just put some benchmarks on this range. So the low end, so why dark matter cannot be lighter than 10 to the minus 21 electron volts, the very lowest mass possible. That's because a particle that is lighter than this would have an associated de Broglie wavelength, given by this famous formula here, which is bigger than the size of a dwarf galaxy, which is typically 1 kiloparsec. So since we know that dwarf galaxies are full of dark matter, if the wavelength of this particle is larger than the galaxy, it would mean that it would spread out and would be excluded. Okay? So it has to be heavier than this just because of the localization of the size into a dwarf galaxy. On the other side, similarly, something very simple, a dark matter particle, a dark matter body cannot be bigger than, say, 10 to the 4 solar masses, just to be conservative. Because indeed, we know that dwarf galaxies, which have a mass of about 10 to the 6, 10 to the 5 solar masses, are inhabited by dark matter particles. And so they should contain at least a 10 or 100 of these bodies, right? So this is sometimes called the incredulity limit. It must be lighter than this in order to have enough bodies of dark matter in a dwarf galaxy. Great, so we have restricted this to these 90 orders of magnitude. Then there are some benchmarks here. So one benchmark is, as I said, that heavy bodies have to be composite and light body can be elementary. There is another benchmark, which is around here, which I already mentioned already, that if it's heavier than, say, a fraction of any electron volt, is better described by a particle. If it's lighter, it's better described by a classical field without a specific conceptual difference. And there is a last benchmark that I want to show, which is around here, so a fraction of a kilo electron volt for the mass of dark matter, which says that the particles which are heavier than this can be bosonic or fermionic. Particles which are lighter than this must necessarily be bosonic. Why is that? Because if I compute the occupation number for light particles here, so this number n, which I can interpret as the density of dark matter, say somewhere like here in the solar system, divided by the density associated to a single particle, so its mass divided by its proper volume, which is the Broglie wavelength to the cube, I find that for light particles, this number is very large. Okay, so light particles have a large occupation number, and so they must be bosonic. Otherwise, Pauli principle forbids you from piling them up in, say, in a galaxy or anywhere where dark matter exists. So this gives you a sort of roadmap of possible characteristics, and this regime is completely unexplored and completely open to different possible candidates. So what I'm going to do in the next 40 minutes is to jump up and down in this range and cover some of the most popular dark matter candidates. And let me start right in the middle here around the weak scale, so the scale of weak interactions, meaning around 100 GeV or 1 TeV, discussing the particles that have been the dominant dark matter candidate in the past 50 or 60 years. So these are famously WIMPs, meaning weakly interacting massive particles. So by weakly interacting massive particles, I mean here particles that interact weakly and have a mass typical of the weak interaction. So say 1 TeV to be precise. By weakly, what do I mean? So there are two interpretations here. Let's say it can be weak in the sense of the weak interactions of the standard model, the SU2 left standard model group, or people sometimes intend it more generally like interactions that are similar in weakness to the weak interactions, but are not necessarily mediated by the gauge bosons C and W of the standard model. So let me be a bit broader. So WIMPs, why have WIMPs been so popular for the last 50 years, to the level that at some point people were saying dark matter, WIMPs, and possibly neutralinos from supersymmetry as synonyms, using the same thinking that dark matter must be WIMPs in a bionivocal way. Well, I think that's essentially because WIMPs are motivated by two main pillars, which are written here, and I will discuss them in a minute. And they have three main practical consequences, which are that can be searched by direct detection, indirect detection, and colliders, as I said at the beginning. So the two pillars are, in some sense, theoretical motivations, and these are experimental motivations. So at some point from the 70s on, the technology was ripe to use this technique, and so people started looking for them extensively, and we have not stopped yet. So let's focus for a moment on the theory part. What are the two theoretical pillars here? So one is the idea of thermal freeze-out, which I'll discuss in a minute. So this is the idea that WIMPs are producing by the mechanism of thermal freeze-out in the right abundance that we need automatically. And this is very striking. So let me show you how it works, although most of you are probably familiar with it. So the thermal freeze-out, a thermal relic from the early universe, means the following. So if I have this famous plot that shows the density, co-moving density of dark matter particles chi as a function of time, so as they evolve in the history of the universe, I have that in the very early universe, these particles were annihilating into states, think of electron positrons, for instance, and also being reproduced by electron positrons in the thermal bath of the universe. So in some way, these particles were at equilibrium with the thermal bath of the universe, and they had a certain abundance. Then, as the universe expands and cools down, the particles chi cannot be reproduced anymore because the energy goes down, and so the thermal energy goes down, and so there is not enough energy to produce the heavy particles with a mass typical of 100 GeV in the thermal bath. So their abundance goes down with the Boltzmann suppression, which is given by this descent here. At some point, when the universe cools down even further and the particles dilute even more, what happens is that even the annihilations of dark matter particles cannot proceed anymore because the particles essentially don't find each other anymore in an expanding universe. So what happens is that their density freezes and it remains constant until the end, which is essentially today. And so this is what we have left over from the annihilations in the early universe. So what we have is a behavior of this way, which can be solved by using the Boltzmann equation in the early universe. So meaning that the equation that describes the density of these particles chi in the early universe. And the final result is, at the end of the day, is that the abundance of dark matter particles chi, so this is the quantity I mentioned at the beginning, is given by just a simple number divided by the annihilation cross-section. So the probability that two particles annihilate, multiplied by the relative velocity. So in order to get 26% of the abundance of dark matter in the universe, which is a number we measure, we discovered that this number here has to be 3×10⁻26 centimeter cube per second, which is the magical cosmological cross-section coming out from this mechanism, right? So if the particles annihilate with this cross-section, they are produced in the right abundance, say about 26%, which is what we measure. Now, the striking observation that people made 40 years ago is that if you compute a typical interaction cross-section for weak interactions, so for particles that interact weakly, you estimate it in the following way. So you will have a weak coupling here and the mass of the particles of weak interaction, so around 1 TeV. And what you get is that plugging in the numbers here, you get precisely of the order of, say, 20%. So weak interactions automatically give you a kind of particles that has the right cross-section to produce the right abundance. So this is the so-called WIMP miracle. Particles that behave like WIMPs are produced miraculously, let's say, in the right abundance. So this is why this pillar is still standing, and it's particularly impressive in some sense. So given that we know that weak interactions exist in the standard model, we also know that WIMPs are automatically a good candidate because their abundance is correct. What about the second pillar? Well, the second pillar is the fact that we are supposed to discover new physics at the TeV scale. So, for instance, supersymmetry or other scenarios had convinced us for decades that we were supposed to find new particles at the TeV scale to solve a number of problems of the standard model that we can discuss. So the current status is that this pillar has sort of collapsed in some sense, meaning that, as you know, the LHC has not found any particle at the TeV scale, has not found new physics yet, only the Higgs boson. So in some sense, we have given up on this possible pillar. But my statement is that this is not enough to dump WIMPs and to get rid of them. Even without a larger theoretical framework justifying them, I think that the thermal production history is something convincing enough to keep the WIMPs as an appealing candidate. And the second point, and on this there is some confusion sometimes in the community because you hear people saying, so the LHC has not found weak interaction, has not found supersymmetry, so WIMP dark matter is dead, let's move to something else. I think this is completely flawed. I mean, it might be the case that we have to move to something else, but not because the LHC has been finding nothing so far. The other point that I want to make is that the three strategies that I was mentioning here are still valid and still have some ground to cover. and are complementary in a way that I will show you in a minute. So let me discuss briefly the status of direct detection for WIMPs and indirect detection for WIMPs before we move to another candidate. So direct detection for WIMPs means essentially the following thing, that we have a dark matter particle floating around in the galaxy, and this dark matter particle can come and hit a nucleus in one of my controlled experiments, for instance, underground. And it gives a kick to the nucleus, and this is the signal we are looking for, right? So this is the principle of direct detection. So in many decades of exploration of this with a number of very well-performing ultra-pure and ultra-screened detectors, we have seen so far no signal of this process here. So what people have done, what different experiments have done, is to put constraints on this plane here. So this is the plane of the mass of the dark matter here. So you see around 100 to 1,000 GeVs is the WIMP scale. And this is the scattering cross-section on nucleons. So the probability that dark matter scatters on a nucleus here. So all these curves come from different experiments and different techniques, and all the region above this curve are excluded, meaning that the cross-section cannot be larger than the regions, the area above the curves. So as you see, these curves are going down and down as the years progress. And right now, the most updated constraint is this one here from the LZ experiment that last year has excluded everything above this value here. So the claim is that there is still room to cover, especially here and here, but we are getting close to the floor, which is this one here, which is given by the inevitable presence of neutrinos coming from the sun and the atmosphere that will sort of make a fog for us too difficult to penetrate. So what are the predictions from the theory? So if I have a dark matter particle that interacts purely weakly, like with a Z boson scattering on a nucleus, then the predicted cross-section is somewhere here, so very, very high, and this is excluded since decades, so since maybe the early 2000s. But if the process is more complicated than just interaction with a weak boson, like for instance, exchanging a Higgs boson or in a loop with different, with W, we can interact with W boson for the weak interactions, then the cross-section becomes smaller and smaller. And in this case, for one loop interactions, is still allowed in this sliver, in this little part of the parameter space. And by the way, I have a very compelling model that sits exactly here, and so it should be discovered very soon, hopefully. So the idea is that this regime is still ongoing. These kind of experiments are still ongoing. And so I would argue that one of the frontiers in this field, from the point of view of experiments and also from theory, is to go as down as possible to reach smaller and smaller cross-section to see if hopefully at some point we do see something. So keep track of this because I'm highlighting a few frontiers, theoretical or experimental, and we'll see at the end where it's better to point. Now, a couple of words on indirect detection for weak interactions. So indirect detection means, again, very basically, that we are going to look for, we are sitting in the galaxy right here, and we are immersed in this halo of dark matter particles here in gray. And these dark matter particles annihilate, exactly like they were doing in the early universe, into stuff. For instance, into charged cosmic rays, say antiprotons or positrons, into pairs of charged particles. So typically you produce electrons and positrons, protons and antiprotons in pairs without violating charge. But let's focus on the antimatter because it's better to beat the background. So these particles, say electrons or positrons, are produced everywhere in the galaxy, and then they have to propagate through the galaxy before they can get to us where we can collect them. And so by doing so, they go through diffusion in the magnetic fields, they are blown out by the convective winds coming from the stars in the galactic disk. They can suffer spalations or shocks in the galactic interstellar medium, and then at some point, hopefully, they will get to the sphere of the sun, and they will be collected by experiments in orbit or even on Earth in some cases. So this is the basic principle of indirect detection for charged cosmic rays. Same works for photons. So if dark matter particles annihilate and produce in some way photons, then we can look at regions where we think that dark matter is densest, in particular, say, the galactic center, and there we can have a flux of photons coming to us, betraying the presence of dark matter. So an enormous number of searches have been done in cosmic rays and in photons, and probably all of you are aware of it. Just to cut it short, I will present the summary, which is this plot here. So this is another plot of searches now for indirect detection. This is again the mass of dark matter, and this is the annihilation cross-section, so the probability that two particles annihilate. So this number here is the magical one of 3 × 10⁻26 that I mentioned earlier. So theory tells you that you should sit here. And these curves are the bounds that you get from different experiments from the known observations of anomalous signals from the galactic center or from the galactic halo in general. So skipping the possibility that some signal, some anomalous signal is actually detected. So you see that from different targets and from different species, you have, roughly speaking, constraints that have this diagonal shape here, from Fermi, from Cherenkov telescopes, or from AMS, so the experiment on the International Space Station measuring antiprotons, and so on and so forth. So roughly speaking, this is telling us that if dark matter particles have a mass of about 200 GeV, then they are still allowed with a thermal annihilation cross-section. If they're lighter, then they're excluded. This region above here is excluded. Okay, so what are the frontiers here? So the experiments are pushing down as we speak, and more sensitive experiments are progressing. And so I would say that the frontiers are two. One is to try to go lower and lower with more and more sensitive experiments, and this is pretty obvious after all. And so pushing this line towards higher masses. And the other frontier, which is more theoretical now, is to consider very heavy dark matter particles, multi-TeV, 100 TeV, even a PeV. So this we could discuss if you want, but let's say that I would argue that this is one of the most interesting possibilities in the near future for a couple of theoretical reasons. Okay, so we are exploring WIMPs also in this case, and we're, for the moment, we haven't found nothing, but we're trying to push the limits down. So that's enough for WIMPs. Let me move to some other possible candidates, and so jump somewhere else on this diagram. The first move I want to make is very simple, and I want to go to particles which are just lighter than WIMPs, something that we call typically sub-GeV dark matter. Okay, so particles which have a mass which is slightly below a GeV, say a few GeV and a bit lighter, between 1 MeV and 1 GeV, or roughly speaking. And what I want to do is to ask myself, okay, so are there similar motivations for sub-GeV dark matter? So are there theory motivations and a compelling production mechanism that points to sub-GeV dark matter like there was for WIMPs? And are there detection strategies that work efficiently, like for WIMPs, in direct, indirect, and collider searches? So let me discuss first the theory, and then we'll see a couple of things about the possible searches, like I did before. So what about the theory? So what are the theoretical motivations to consider sub-GeV dark matter? Well, actually, I think the first idea of sub-GeV, or actually MEV in this case, dark matter particles, so particles with an MEV or sub-GeV mass, goes back to these people, Céline Bohème and Pierre Fayet, working not far from here in École Normale, that as early as 22 years ago, were saying that actually if dark matter particles they can be significantly lighter than the few GeV, so basically the WIMPs, if they are coupled to a new light gauge boson or to some other kind of interaction. So they were the first ones to point out that dark matter particles can be naturally lighter if they interact not weakly, so going out of the Wink obsession, say, but with some other new force, a new gauge boson, and that at the time was called a dark boson or something like this. So this idea stayed there for a while, and then it was sort of revamped a few years later in what is called now the WIMP-less dark matter idea. And this is by Feng and Kumar in 2008. Roughly also connected to hidden sector dark matter or secluded dark matter. These are all sort of synonymous for my purposes of the same idea. And what is the idea? Well, the idea is very simple, and it is that I told you before that if I want to have the right abundance from cosmology, from the production mechanism, I have to have this annihilation cross-section at the right amount, right? The one that produces the thermal freeze-out. And in the case of WIMPs, this comes out because the weak coupling divided by the weak mass has this typical ratio here that gives me what I need. Now, the idea is super simple, and it's to say, okay, but if I have another kind of interaction with a different coupling and another kind of mediator with typical scale of interactions with another mass, call it small m, I can have the same value and so obtain the same abundance within a different scenario. So I don't necessarily need weak interaction numbers here, but I need something for which the ratio is correct. So as I wrote here, if G is the coupling of a new force, say a dark boson in some way, which is smaller than the weak interactions, then the mass of the typical scale of particles can be smaller, and the miracle works anyway. So this is the so-called WIMP-less miracle. So in this case, I do the annihilations exactly like I did before in that plot. And what I get is that the particles of dark matter annihilate through this GX, actually should be GX here, into these new bosons, new mediators called phi, which then in the end will couple to standard model particles in some way. So by doing the thermal freeze out exactly like I discussed before for these kind of interactions, these new interactions, then I get the right abundance. So this shows you that the WIMP-less, so the mass can be different just if you have, and also in particular sub-GeV, in case you have new forces coming into play. Yet another idea for sub-GeV dark matter particles is the following one. People call it the SIMP miracle. So these are models, these are scenarios in which you have the dark matter particles interact in a weird way. So no more annihilations into standard model particles, but the relic abundance is set by the annihilation of 3 dark matter particles into 2 dark matter particles. So it's a sort of self-annihilation of 3 particles into 2 particles with a specific effective coupling here. So if you do exactly the same analysis as before, you solve the Boltzmann equation as done before, you find out after a while that this points to a mass given by this combination of parameters, which is of the order of 100 MeV. So exactly like before for WIMPs, the mass was naturally the one of weak interactions. Here instead, you have a mass which is sub-GeV in sort of miraculous way also in this case. And you can build up models in which this is naturally realized, for instance, in a dark QCD-like group. So a group similar to QCD, but in the dark sector, where you have large couplings of the order of even 4 pi. So this points to sub-G masses again. I forgot to say that these are models that go back to Leonid Hochberg and collaborators about 10 years ago. So more generally, people at some point started considering, in general, simplified dark matter models, light dark matter model, which means just considering, in general, the possibility that dark matter interacts in some way via some extra field, which this phi here, which can be hadrophilic, so coupling especially to hadrons, in this case, the top quark, and it can be a scalar or a fermion or something else. So let not me go into the details back here, but just to show that there is a whole industry of people considering sub-GeV dark matter, as you see in these ranges here, using these simplified models of different sorts. So sub-GeV dark matter is interesting, and people are exploring it since about 10 years or so. So the theory motivations, if I have to summarize for sub-GeV dark matter, are these that I listed. So WIMP-less dark matter, the SIMP miracle, MEV dark matter, or simplified in general models, or asymmetric dark matter, which is not discussed but goes back to the same range of masses. So you see there are enough possibilities, enough motivations to consider this kind of models. So to me, this is less compelling than the WIMPs. So as a matter of taste, I would say that this is less convincing than the WIMPs. Why? Well, simply because we know that weak interactions exist in nature, while we don't know whether a new force exists in nature. But if the new force exists in nature and has the right properties, then these possibilities are all viable. So I would say that the theory motivation is mostly why not. So we should look also for sub-GeV dark matter, because after all, WIMPs, we're getting close to exhaust the searches. So let's see how we can look for them. So direct detection and indirect detection in particular. So direct detection first. Direct detection, the idea is still the same. So you have a dark matter particle coming in, hitting a nucleus and giving it a kick, and so giving it a signal. But the problem here is that the energy, if the mass of the dark matter is very light, then the energy that it can deposit into the nucleus is very small. So you have that basically you are below threshold for your experiment. The nucleus doesn't even move if it's hit by a very light particle. Like you try to hit a bowling ball with a ping pong ball, it doesn't move at all, right? So you will be below threshold for this kind of nuclear recoil experiments. So indeed, if you see this plot that I showed before, when you go to sub-GeV masses here, then the limits go up very much by orders of magnitude because you are below threshold for these experiments. So here there are a number of new ideas which are to look for electron recoil signals. So the dark matter hits an electron instead of a nucleus, or looking for the Migdal effect or other experimental strategies that we can discuss if you want. So I would say that this is a new frontier. So people are pushing with many experiments into this direction. And actually, last week, there was a paper by the DAMIC collaboration, so from our friends at LPNHU in Jussieu, that actually has the most stringent bound right now somewhere here. So people are pushing towards this regime of sub-GeV dark matter masses in direct detection. And what about indirect detection? So indirect detection means, as I said before, that you have to look for charged particles, for instance, coming from the annihilation of dark matter particles in the galaxy. But there is a problem in this case. So if we are looking for sub-GeV dark matter, it means that the particles which are produced, so the electrons which are produced, let's say, have an energy which is below 1 GeV, clearly, so they are not very energetic. And so when they travel around the galaxy and get to us, they cannot penetrate within the heliosphere of the sun, because the sun acts as a screen and the magnetic field deflects the low energy positrons, say, and protons which are trying to come in. So you will not see particles coming from the galaxy due to this system here if the original dark matter particle is with a mass of below 1 GeV, roughly speaking. So our experiment cannot collect them. There is only one exception, which is the Voyager spacecraft, which was launched in the 70s, actually the same year I was born, and is still sending back signals in the same way it has been doing since 49 years. And it's outside of the solar system. So it's outside of the solar sphere of the heliosphere of influence. So it means that actually Voyager is detecting possibly electrons and positrons and other stuff coming from dark matter particles, and so it can impose constraints on these exotic mechanisms. And we will see later where the constraints lie.
Yeah, naive question. Sure. These charged cosmic rays, they cannot be accelerated. I mean, here you say they've been produced by a light particle.
Yes. So I'll show a plot later where you actually include acceleration. I'm not considering that in the sense that it's, let's say, when they hit the interstellar medium, they can be accelerated just by, as usual. And in that case, they can penetrate the source of the sun. But then it becomes less model independent in the sense that you have to rely on some sort of acceleration. I can show you a plot later where this actually happens. If it doesn't happen, then it's only energy losses here, and so they cannot penetrate. The other possibility for indirect detection, as I said before, it's not charged cosmic rays, but photons, right? So if I have sub-GeV dark matter particles, they produce clearly sub-GeV gamma rays, sub-GeV photons. And what is the problem with that sub-GeV photons? Well, the problem is that if I look at the current sensitivity of experiments, this is depicted here. So as a function of the energy, This plot describes the sensitivity of all different experiments currently operating. And what you see is that for high energy, say above a GeV, there are very efficient telescopes such as Fermi or the Cherenkov telescopes here. And for light energy, there are typically these are X-rays. There are efficient telescopes such as these ones here, Integral and the others. But in the middle, there is nothing. Okay, so let's say that people call this the MEV gap. So below roughly a fraction of a GeV, there are no sensitive experiments that can be there to measure these sub-GeV gamma rays. So we are hitting, so there are past and current experiments like Integral, Comptel, and Fermi that are very good either at large energies or at small energies, but not very good here in the MEV gap. Yes?
Swift is can detect in MEV.
Swift?
Yes.
Okay.
And it's I mean, sensitivity
know where
is quite large.
Yeah, I don't know where the sensitivity sits. If you have the other, so what I'm not saying here is that what we need is to be able to measure a diffuse flux, so from large regions of the sky. So if it's dedicated only to one spot or to specific sources, then it becomes an issue.
Swift at each moment can see about 0.2 fraction of the sky.
Great. Then I was not aware of it, and it's probably very promising. We can have a look at it. Yeah. So what we consider in a moment, I'm going to say that we consider other experiments, not including this one. NuSTAR, XMM Newton, Suzaku, Integral as well, but not this one. Okay, great, thanks. So my point is that here you have a little stuff, and so what you have to do is to find a trick to be able to see sub-GeV dark matter particles, not through the sub-GeV gamma rays that would fall in this gap, but through another technique. And this other technique, and I'm not going into the details, although I could spend an entire seminar on that, is to search for X-rays, so much lower energy gamma photons. The idea is that the electrons and positrons produced by these sub-GeV particles in the galaxy, they make inverse Compton scattering, ICS, on the photons of the galaxy, say the CMB or starlight, and they produce X-rays. So X-rays will fall somewhere here, and these will be able to see. So by using these experiments, we'll be able to overcome the gap, which is in between. So this is the content of these few papers that I did recently, and a few updates also, which are here on the screen. So if I put everything together concerning sub-GeV particles, what do I get? So this is, again, the space of dark matter mass and annihilation cross-section. This is now in MEV, so this is 1 GeV and this is a sub-GeV. And you see, so this is a busy plot. There are many, many things, but let's focus on two things. One is the Voyager constraints, which are here. So they are pretty interesting. And the other one is the X-ray constraints, which are those that I just mentioned, coming in particular from XMM Newton here, which are here. So they will be able to, they are able actually to constrain sub-GeV dark matter masses of the order of, say, this annihilation cross-section. All the other bounds, we can discuss them. They're very interesting. They apply under certain conditions. Okay, this is just to say that there is a lot of research there. So what is the frontier here? Well, very clearly, we are pushing with the experiments in this direction to be more and more sensitive to this kind of models here. So let me pause for a moment and go back to this plot. So I mentioned the plot on the constraint on the WIMP interaction. So now this is again the weak scale. I mentioned these constraints earlier. And the idea that Arpan had a few months ago is to use the same trick that I just discussed and use the inverse Compton scattering from WIMPs now to probe them using MEV telescopes. Exactly the trick that I discussed a minute ago can allow you to improve the constraints with respect to those that are shown here. So this is the plot we produced last month. So actually this month. So these are the green ones are the same constraints that you see in this previous plot, just taken all together. And we show that with these upcoming experiments, AMICO, Iastrogam, and MAST, we will be able to probe an area which is much below, several orders of magnitude, and even cover most of this regime of thermally produced dark matter here. The trick is exactly the one I was mentioning before, so looking for inverse quantum that gets you out of the typical range of photons that people explore. Okay, so let's move on, and we have been discussing sub-GeV particles. Let me now change now for something completely different. Let's go to the very large masses, and so in particular consider primordial black holes, which are these PBH selected here. So why primordial black holes? We were discussing earlier with upstairs. So how can dark matter be in form of primordial black holes? We have been taught in school that dark matter cannot be a weird astrophysical object such as black holes or brown dwarfs or rogue planets or stuff like that. We have always been told so. Essentially because you have the phenomenon of strong lensing. So there have been many searches, many surveys looking for strong lensing, which essentially means the following. If dark matter in the galaxy is made of black holes going around, then if you look to a distant source, such as the Magellanic Cloud or an outer galaxy like Andromeda, you could get that the light sources from that source gets distorted, strongly lensed, whenever one of these bodies passes around, right? And so this imposes some constraint on the presence of these large bodies in the galaxy. There are actually very stringent constraints. So this is the mass of these MHOs, so massive hollow compact objects, massive compact hollow objects in solar masses here. And these are the fraction, this is the fraction of dark matter which can be made of these weird objects like, say, black holes or brown dwarfs or big planets or whatever. So you see that roughly in between 10 to the minus 11 solar masses and 10 to the 3 solar masses, they cannot be more than a few percent of, they cannot constitute more than a few percent of dark matter. And this is as recent as constraints from last year from this Ogle survey that looked indeed I think at the Andromeda galaxy. So very much constrained, as we have been taught in schooling. Yet there is another thing that tells us that dark matter cannot be made in terms of black holes, and it is that after all, black holes, when they are produced from stars, they are made of baryons, right? So the collapse of stars is essentially the collapse of a cloud of baryons, hydrogen, helium, and so on. But we know that dark matter cannot be a baryon of the standard model from cosmology. So the BBN nucleosynthesis tells us, computes the abundance of helium based on the abundance of primordial baryons. And if the baryons are more than what BN tells us, we would have a universe full of helium, which would not work. And it's the same way the CMB tells us that the baryons are at most 4% of the total, while, as I said earlier, we need 26% of the total. So this, for decades, meant that people were not considering candidates other than the exotic particles that I discussed before. But there is a loophole, which is this one, which is primordial black holes. So if these black holes are produced before BBN, then they are removed from this count here, and so they can work. And if they have a mass which is either too small or too large to do the lensing, then they can be still allowed by the stringent constraints that I showed before. So the motivation for this was proposed by people, including Hawking in the 70s, but then was sort of forgotten for about 30 years, and actually even more, and became more popular again when gravitational waves were seen for the first time, because they were merging of black holes with weird masses, let's say, and so people started considering that the LIGO Virgo events could have been primordial black holes rather than standard stellar black holes, astrophysical black holes. Then it took a life of its own, and so now it's again a popular possible candidate, but it comes from this motivation originally here. So indeed, dark matter can be made of black holes, assuming that they are primordial, and so they go around these two constraints, these two no-go theorems, say, that we have always been considering. So let me show you the current status of this. So this is the mass of these machos or primordial black holes, again, in grams or in solar masses here. And this is the fraction of dark matter that they can constitute. So you see, these blue things are the microlensing that I showed before, just in log plot, shown here. And then there are other constraints that enter in the large mass, and in the small mass here. So I'm going to discuss in a minute this small mass here. But what I want to show is that this window is still open, right? So primordial black holes, or in general machos with a mass in between 10 to the minus 16 solar masses and 10 to the minus 11 solar masses, can constitute the dark matter. If you check, this corresponds to about the size of an asteroid, a big asteroid, or Mount Everest. So if you have black holes with the mass of a big mountain floating around in the galaxy, then they can be the dark matter. The mass is large, but the size is minimal, so it's smaller than a proton. So very dense, of course. They are black holes, but rather heavy, like an asteroid. So this is a window which is still open for dark matter. Let me discuss very quickly the constraints. So the constraints come from a number of, so if dark matter is made of primordial black holes, then there are the range of sizes is huge, as you can see here. It's roughly given by this formula here. So this T is the time of production. If it's produced very early, you have a very heavy particles. If it's produced very late, you have very light bodies, very light primordial black holes. And there are different constraints. Let me show you this one here. So the primordial black holes, since they are black holes, evaporate. So they emit energy, they emit stuff by Hawking evaporation, like any black hole. And if they are small, this evaporation can be significant in the sense that the temperature of the evaporation is inversely proportional to the mass. So if the mass is light, so for astrophysical black holes, this is always irrelevant. But for light black holes, then this mass can be very much lower than the mass of the sun, and so the temperature can be high, and so you can have a significant emission. So the evaporation can happen at a rate of the order of given by this formula here, which is inversely proportional to the square of the mass. So the smaller they are, the more important is their evaporation rate, with a spectrum which is typically a gray body spectrum, similar to a black body spectrum, which is given here. So if the black holes are too light, then they evaporate very quickly, and they would have evaporated already by now. They are produced in the early universe, and they evaporate much earlier than today. So this is the red part, which is excluded here. If the black holes are instead, say, a bit heavier, then they are evaporating right now. And so they are producing energy, they're injecting energy, they're spitting out stuff right now. So this is what people are looking for in all these different techniques here. So let me mention just one of them, which is this one here. So this line, which corresponds to the name Voyager here. So the idea is very simple. So if the galaxy is filled by primordial black holes, and they are producing electrons and positrons by Hawking evaporation, then, so at low masses, so low energy, then Voyager should have seen them, because it's outside of the solar system. And this is indeed what we tried to look at a few years ago with my postdoc Mathieu Boudou at the time. So these are the data by Voyager, measured in 2015, I think. And these are the signals. Look at the red lines only for the moment. So these are the signals, the emission of positrons and electrons produced by primordial black holes with this mass, 10 to the 16 grams, or 10 to the 15 grams, or 10 to the 17 grams. So what you see is that if a primordial black hole is heavier than 10 to the 16 grams, then it overshoots the Voyager data. So this is not allowed. Postscriptum, this is should be fine. Postscriptum is the blue line is what you get in case of reacceleration. So if you accelerate these electrons and positrons with some weird mechanism, then you can have huge extended lines like this, but let's not go into that. So if you stick only to the non-reaccelerated case, then this is what you get. So this imposes a bound to the maximum mass of primordial black holes that you can get. And indeed, it gives you, this is a zoom of the same plot as before, mass of the order of 10 to the 16 grams or 10 to the minus 17 solar masses. These are the constraints that you get within the same, within some assumptions. So if they cannot be lighter than this, otherwise they produce too much electrons and positrons, and Voyager would have seen it. It's a fun fact. I will cite that this paper had some coverage in the press. So the way science puts it is that the aging Voyager 1 spacecraft undermines the idea that dark matter is tiny black holes. And the way that Forbes puts it is that Voyager opens a new door to look for dark matter. So I think I agree more with the science interpretation of the thing, but if I find a billionaire that is helpful, that is willing to finance my next postdoc, then Forbes is perfectly okay. Okay, so the other frontier then is that people are trying to push this regime to see if you can close this window in some way by looking at more sensitive experiments and lower and lower energy, lower fainter and fainter Hawking emission. There are challenges there, and we can discuss if you want. Now, in the last 5 minutes, or even less, I'm going to cover the last 2 candidates. So let's jump back and jump to KeV particles. So KeV dark matter, kiloelectron volt dark matter, so light waves. And in particular, let's talk about sterile neutrinos. So this is a candidate for dark matter, which is motivated, at least in one way of seeing things, very phenomenologically by the fact that in about 10 years ago, in these 2 independent papers here, a number of researchers have found an excess in X-rays with an energy of 3.5 or something keV. So in this paper here, it was coming from a number of clusters observed by Chandra and XMM Newton with a certain redshift. And in this paper here was coming from Andromeda and from the Perseus cluster with this range of redshifts. So in these plots here, you see the raw data, and you are supposed to see the line coming up here at about 3.5 keV. So the significance, despite the fact that the plots are busy, the significance, statistical significance is pretty high for sigma or more. And actually, we had an overview of this in the seminar by Stefano Profumo in December, I think, because he has worked a lot on this. So one of the possible interpretations for these anomalous signals coming from these clusters and these galaxies is that there is dark matter contained in it in the form of sterile neutrinos with a mass which is 7.1 keV, so twice the mass is twice the energy of the line that we see, which is decaying, so which is decaying with a half-life which is very long, but not zero, but not infinite, which is this one here, so 10 to the 29 seconds. The diagram by which this happens is that the sterile neutrino mixes with an active neutrino, and so it can emit a photon and an active neutrino, standard model neutrino, via this diagram here. So again, people here are looking in this parameter space of the sterile neutrino mass and the mixing angle, which determines how frequently this diagram happens. This is the current interpretation of the excess, and these are the current constraints from other sources showing that maybe we are a bit in trouble here, and this excess is actually already ruled out. So yet again, here is another frontier. So people are trying to push in this way with new experiments, new satellites, including a Japanese one, and so on and so forth. And the last thing I have to discuss are ultralight particles. So this is a huge domain, so I'm not going to touch it at all. I'm just going to give the very short summary, which is that these particles, which typically are called axions or axion-like particles, are theoretically motivated because one can add to the standard model of particle physics this Lagrangian term here, which is exotic, say, but contains these parts. These are the gluons, essentially, and this is a coefficient in front called theta. And this extra term induces a dipole moment for the neutron. So the neutron would have, being neutral, would have a little bit of a charge asymmetry between plus and minus of the order of this value here. So 10 to the 16 times the free parameter theta E per centimeter. The problem is that experimentally this quantity is constrained to be very small, smaller than 10 to the minus 26 E per centimeter. So it means that theta has to be smaller than 10 to the minus 11 to make this work, right? And so the question in the particle physics is, why is this theta so small? Well, maybe because the answer is maybe because theta is actually a dynamical quantity, so it's actually a field. And this field is driven to almost zero by some potential called the Péchet-Quinn potential, which is under this symmetry here, U1. So this is a summary of like 30 years of work by these people here. This is to say that this predicts that this field exists, and let's call it axion, with a mass which is typically of a fraction of a millielectron volt, so a very light one by this normalization factor here. So people are looking for very, very light particles here, which could consist which would come from this mechanism in a number of ways that I'm not going to discuss at all. So looking at astrophysical systems, looking at decays in the extragalactic decays, and so on and so forth. So here, the frontier is that people are trying to push this one down as usual to go to lower and lower couplings between the photons and these particles here. So to conclude this walk over 90 orders of magnitude, I discussed thermal dark matter, I discussed sub-GeV dark matter, I discussed primordial black holes, I discussed KeV dark matter, and I discussed ultralight particles. And this covers more or less all the rough categories of ideas that people have been considered. So what are the conclusions? But my conclusions are the following, that the physics of dark matter is currently in an experimentally driven phase. So we're looking everywhere for clues. And for the moment, we have many of them, but no clear avenues. The theory does point to some preferred directions, but maybe actually too many, in the sense that there are so many ideas that this is going into many, many directions. So if I have to give a short summary, thermal dark matter is still motivated, as I said. WIMPs say the frontier is to look for heavy dark matter. Sub-GeV dark matter is a why not, but detecting them is challenging. Primordial black holes is an old idea, but it's becoming more popular again. This open window still available. KeV dark matter is phenomenologically motivated, so why not again? And also for axions, it's an old idea, goes back to Péchet and Quinn in the 70s, but with new interpretations. So for those who have been keeping tracks, these are the directions of the frontiers, the searches for dark matter. Goes a bit in all directions, which I think is very healthy and it's very exciting in some sense, because we have to look everywhere from an experimental and a theoretical point of view. I also have a frontier up here, but only if people are interested. Okay, thank you very much.
Questions or comments?
Yeah.
In the higher mass limit of dark matter, you discussed the interaction with protons, nucleons, and so on. However, let's consider that the dark matter interacts only with neutrinos. Is there any limit?
Yeah, so I can show again this summary plot, and you will see this one. So this is the scenario is the one of annihilation of dark matter particles into stuff. This stuff can be protons and antiprotons, and you get these limits here. It can be photons, and you get this. If it is neutrinos, then you get these limits here, the dotted ones. You see them here. So they are relevant, but only at very large masses. So beyond actually this mass here. And the reason is that so, okay, on one side, detecting neutrinos is more difficult because we need huge experiments, fine. But the advantage of neutrinos is that you see that these bounces stay flat, right? Instead of going in this way. And that is because so more heavier particles of dark matter produce more energetic neutrinos, and the cross-section of interactions of neutrinos with the experiments goes up with energy. So this compensates the fact that for large masses of dark matter, the density goes down. And in the end, the bounces stay roughly flat. So as you get to about 100 TeV, they become more important than gamma constraints. Or from some specific channels, such as annihilation into muons, they are, you see here the green, they are more relevant than the others. So these are bound from Antares, from IceCube, SuperCamioCande, and soon from KM3Net and the others.
Concerning the direct detection experiments for dark matter, do you think that even if finally no dark matter particle has been observed yet, do you think that the detection and analysis of the neutrino floor, which is almost closely to be detected by these experiments, is worth all the efforts which have been made in building these experiments?
Yeah, that's a tough question. So, two things. Yes, so we have first of all to get to the floor. And this is not, so this is a log plot, so this is one order of magnitude, so it will take the next effort called Darwin or the new experiments, which are multi-ton experiments of liquid gas to get down to here. So first of all, it's not trivial to close even this window here first. Second, here there is a huge space. So going down here, before we get the neutrino, we touch the neutrino floor, it will be difficult as well, and it will require a lot of effort. So here there is a lot of work to do. And the third thing is, even when you touch the neutrino background, and people, actually some experiments have already touched it, it was in the news 6 months ago, Xenon and Panda X, then you can try to work to go beyond it, to go under it. And the idea is very simple. So if you know well the shape of the background, so if you know what you expect from neutrinos coming into your experiment, you can subtract it and look for excesses, like we have been doing at the LHC for decades, or in particle physics for decades. It's much more complicated because here we are dealing with rare events and not huge numbers like in colliders. But one can try to model a background and model the neutrino background and throw it away and see what's left. So the fourth now hope is that you can use directionality. So the neutrinos come mostly from the sun. So if you see the flux coming from the sun, I mean, if you see events in your experiment, you remove all those that come from the sun that you assume are due to neutrinos, and you keep only the others, which could be coming from instead dark matter interactions. So using directionality, you can discriminate the signal from the noise. It's very difficult, but there are many experiments not many, but say 5 or 6 experiments working in that direction. So I don't think that our colleagues are out of work for the next 20 years.
One question. Can you tell a bit more about the motivations for heavy dark matter? You said you seem to have some.
Yeah. So where is it? The idea is that heavy dark matter here means to me, say above 10 TeV to a PeV, roughly speaking. And there are 2 motivations mainly. One is that there is something that is called the Sommerfeld enhancement, which means that the weak interactions. We are talking about WIMPs here. Weak interactions, when the mass of the particle is very large, so beyond 10 TeV, the mass of the bosons, the Z and the W, becomes essentially 0. Effectively, it's like they are massless particles, massless mediators. And this mediates an enhancement, a strong force that enhances the annihilation, a bit like if you are interacting through photons, which are massless. So this is the so-called Sommerfeld enhancement. So it pushes the annihilation cross-section up because it's more effective and so it's more annihilating. That means that to have the same amount of dark matter in the galaxy, you have to have heavy particles. So the Sommerfeld enhancement pushes you to heavy particles. Okay, this is one argument. In some sense, naturally, and Sommerfeld enhancement necessarily exists for WIMP models. The second argument is that, okay, this is a bit more model dependent, but we have explored simple WIMP models, like the neutralinos and so on. If we consider more complicated WIMP models in which you have more particles in the multiplet, this also creates more annihilations, because if you have like 4 or 6 particles in this multiplet, they can co-annihilate among themselves. So larger cross-section, which pushes you to heavier masses. So, okay, I understand it's a bit involved, but the argument is the natural ingredients of WIMPs imply large cross-sections, and that implies being pushed to large masses. So it's possible that something sits here. Yes.
So what is the motivation given the next generation of colliders, the future circular collider, to get us up to 100
the question. Yeah.
helping us detect perhaps evidence for supersymmetry or dark matter candidates, whatever?
So since I'm not recorded, I will say that I don't really believe that the future colliders are a machine to produce dark matter, as they are sometimes sold. Okay, so people say, okay, the next frontier after the Higgs boson is discovering dark matter, and we need to build the next collider at CERN, 100 TeV and so on, to discover the next big unknown, which is dark matter. I don't think there is a strong enough scientific case for that, to be honest. Okay, because even, I mean, if you look at these regimes here, even 100 TeV collider will not be able to produce it. That does not mean that the 100 TeV collider is useless. Absolutely not. I mean, every time we build a bigger collider, we discover something, and so science advances in this way, and we should actually do it. Okay. There have been discussions in the newspapers and in the strategic discussions in Europe and so on. But the fact that it's sold as a dark matter discoverer, to me, is not very compelling. I cannot see a clear model case.
A slight variation on that might be as a discoverer of supersymmetry, which has had, remarkably compelling arguments in the past. Do you think is that an option still? Or?
Okay, again, this is a sensitive subject. So if you ask me, no, in the sense that if we discover supersymmetry with a typical mass of supersymmetric particles at, say, 10 TeV, currently the limit is 3 TeV. Okay, so supersymmetry, simply put, does not exist below 3 TeV. Suppose that we discovered particles at 5 TeV. That means that still it's much larger than the typical scale of weak interactions, which is 100 GeV, the mass of the W boson. So there is a gap between 100 GeV and 5 TeV, which, since it goes to the square, which corresponds to a new hierarchy problem. So people have been introducing supersymmetry to solve the hierarchy problem of the standard model. So why the Higgs is so light with respect to the Planck mass? To solve that, we introduce supersymmetry at a low scale. But then if now this scale goes up again at 5 TeV, we still have a gap. Not as big as the one before, so less embarrassing, but still very big. So the motivation for supersymmetry, to me, honestly, unfortunately, is a bit gone from this point of view.
Yes.
Yeah, I was interested in the discussion about super heavy dark matter model. So beyond the PV, I don't know if you have an opinion on this.
So beyond the PV, even higher than that. So there is one main issue, which is if you go. So I have not the plot here, but you can find it somewhere else. So if you go above 300 TeV, okay, you have an issue with annihilating dark matter, so dark matter produced by annihilation, which is called the unitarity bound. Okay, so heavy particles cannot annihilate efficiently enough to be the dark matter. So typically people stop at 300 TeV. If you go above 300 TeV, you can have two cases. One is dark matter that actually is produced in some way and manifests itself by decaying, not annihilating. So heavy dark matter, PV dark matter, can decay into stuff and be seen in the experiments. If then it has a mass of 220 PeV, then you see it in ImageNet and we are happy. But in general, it has to be decaying and not annihilating. The other comment I can make is you can push this barrier of 300 TeV a bit farther by having non-standard cosmologies of some sort. So if you have some mechanism that dilutes the abundance of dark matter in some moment in the early universe, then you can afford to have more heavier particles without hitting the unitarity bound. There are models on that, and we can discuss. I mean, it's a sort of theory motivation to push it a bit above. It's not so natural. You need to work a bit. But as I said, we have looked into this regime for decades. Let's go and look somewhere else also.
All right. Well, let's thank our speaker, Marco again.